Hello everyone, this is S. Roy. Let's start our Haskell module, and today we'll start with part 1. Let's make it bigger, and this is the list of topics. And first we'll have introduction to Haskell. This will be our new language to learn. An overview, we already know that Scala is like a bridge between object-oriented paradigm and functional programming paradigm, right? And in contrast, Haskell is fully functional programming language. So that means it is inside functional programming paradigm. And we'll learn that Haskell is also called pure functional programming language. And we'll see with example that Haskell encourages a style that is called whole meal programming, where we give stress on the what part, not on the how part. That means what is more important than how. We'll see. Haskell also supports lazy processing. As an example, Haskell can work with infinite list. That may sound crazy, right? How can we work with an infinite list in a computer? And the trick is by lazy processing. That means we will have an infinite list, but we will only evaluate those items in that list which are necessary at the current moment. And with that philosophy, we'll be able to virtually work with an infinite list. And this is called lazy processing, very important. A little bit of history. Haskell was born in 1990 and it was again revised in 1998. A lot of mathematicians and theoreticians as well as practitioners are very excited about Haskell. Haskell supports pure functional programming. That means it does not allow or it does not cause any side effect. Correct? And the reason why Haskell does not cause any side effect, that is because of its strict policy in writing function. So in a pure functional programming, if we give same input parameter to a function, the output will be always same. So this is like a strict contract, and that helps Haskell to guarantee that there is no side effect. Now let's talk about what we mean by whole meal programming in Haskell. Before going to Haskell, the red code snippet is from C++ or Java. If you see what's happening there, you can figure out there is a list, right, LST, and we are traversing over all items in that list using a for loop. There is an iterator, I, index. We are incrementing the iterator in each iteration, and we have an accumulator variable which is mutable, and we are updating that accumulator variable in each iteration, and each time we are accumulating 3 times the current element. So what will be the effect? The accumulator final value should be equal to the total of all elements multiplied with 3, correct? Some experts looking into this red piece of code feel unhappy, and they call it indexitis. A lot of indices are getting used, right, unnecessarily. And on the other hand, Haskell writes the same code in a totally different style, and that is shown in this blue part. So here is the list. We use map and we apply this anonymous function 3 star with the map on this list, and that can basically multiply 3 with each element in that list, right? And that will also result in another list, and then we'll apply another function on that list, and we'll get the sum. So if you see here, we are working with the whole list, not with one ith element of the list, and that's why it's called whole mill programming. Hope we got the idea. Now let's talk about the type system of Haskell. Like Scala, like Java, Haskell is a strong type language, and as well as Haskell is a static type language. If you remember Scala, Scala also does type inferencing, correct? We saw that. Haskell is also very strong in type inferencing. So Haskell code may not look like a static type code, but using type inferencing, Haskell figures out all the types at static time. And in the community, Haskell type system is considered the best among all other functional languages. So type system is a very strong point, is the strength of Haskell. We'll also see that Haskell type system allows polymorphism, and that results in very clean code. We'll see that. Now, some little examples with numbers and characters. Whenever we start learning a new language, we always do that, right? So let's get to Haskell interpreter. This is the symbol of the Haskell interpreter we just started, and we are typing 4 plus 2 multiplied with 5, and as we expect, the result is this, and we can see there is integer, there is double, and the result is double. That makes sense, right? It's as expected. But when we do a string and plus another string, Haskell gives us error. And if you look into the error, it somehow tells us that by just looking into this, hello, Haskell figured out it is a list of characters. So this, whatever we type, that is a list of characters. And it says that, hey, you are trying to treat this list of characters as a number because you are trying to do addition, which is only allowed for number, and no such thing is available in Haskell. So that is actually the meaning of this error. So that indicates that Haskell is strong type system, right? And if you are interested to concatenate two strings, you have to use plus plus. Like Scala, we use plus plus to concatenate two strings, right? And in Haskell, string is a list of characters. You can also type left bracket, then single quote A, comma, single quote B, right bracket. So that means a list of 2 characters, right? And Haskell tells you that that is exactly same as the AB string. So this somehow proves that in Haskell, a string is nothing but a list of characters. Let's work with some Boolean variable and let's check equality. So 4 plus 5, if you type that on the Haskell console and then equal 9, of course Haskell will say it is true. And on the other hand, if you type 5 plus 5 and then slash equal, that is not equal symbol in Haskell, slash equal. So 5 plus 5 not equal 10, which is not a true statement, right? And that's why Haskell returns false as the evaluation of this expression. Now let's type if in Haskell. So if 5 equal 5, then true. But surprisingly, Haskell gives parse error. Why? Because Haskell does not accept an half if. We have to always say the full cases. That means if this is true, then this, we have to also mention what is the else case, and that can be false, and then Haskell is happy, and in this case it is evaluating the above as true. Okay, so to check the strong typeness of Haskell, we can do more. If you type if 1, so instead of Boolean variable, we are typing 1. which is acceptable in C, C++, right? But Haskell says that, hey, I don't treat a number as Boolean. Okay, so that is not available. And if you want to add one number with a string, Haskell says that, hey, a string is a list of characters and I cannot treat that as number. Now, some type inferencing in Haskell. So if you just type 5 on the Haskell console, it does not tell you any extra information. But if you want to know what is the type of 5, you can type :t, then 5. So :t stands for type information of 5. And then Haskell said that, hey, A is a number type, and what you typed, this 5, that is like A. So that means, in other words, you typed something like a number. And then, I mean, what I'm doing here, you can, instead of typing this :t again and again, you can just set this configuration that, hey, I'm interested in type information. So :set plus t. Then from now on, whatever you type, Haskell will try to show the type information. So it is telling you that, hey, this 5, what you type, that is like a number. And also then here we are typing hello, and it is telling that, hey, hello is like a list of characters. And here, whatever we typed, that is nothing but a Boolean. Makes sense, right? Okay, now let's move to some code elements of coding. To get a variable in Haskell and give that a value, it's very simple. So if I just say x equal to 10, that actually defines a variable x. And mind that you can never change the value of x. I think we already expected that in Haskell everything is immutable, right? And that is the characteristic of pure functional programming. So the value of x will be always 10. And then here we are giving 5 to value, variable r, and then area is equal to that is just like an expression on the right hand side. So area is also a variable. Okay, now mind that the next line defines a function, and the function name is double. X is the parameter of the function, and the right hand side, which is on the right of the equal symbol, that is the body of the function. So what does it say? Given a parameter x, the function is going to multiply that with 2 and return that, and that is the meaning of double. So double is the name of the function. So try to compare that with Scala. Scala also had this equal symbol and then body, right? That is same, but Scala has a def keyword. Haskell, we do not need the def keyword. Okay, so how to use the function? Of course, name of the function and then give the parameter, and Haskell is returning 4. Now, of course, not always we can type things on Haskell interpreter, right? Our code can be longer, and we may need to type it in a file and then load the file from interpreter. So here is a small example. So you can always start with module main where and then can write the code. But mind that it is not mandatory. You can also just write your code, which is this is the code which defines the function, right? But if you type this first line module main, then you are required to type another main method, which is the small main, and then you can say print and then call this function with the parameter say $2. So this will calculate what is the value this function returns with parameter 2. So that will return 4, right? So it will print 4. So mind that if you have the first line, then you need this third line main. But if you just write this second line, then that can be okay as a valid Haskell code file. Okay. Now, after you save it in double.hs, how to load it on your interpreter? You have to type :load, then that file name, and that will compile things, and then you can call this function double with any parameter, as an example 5, and it returns 5, right? Now you can do extra in your code. So here, not only I'm defining this function double, I am also specifying what is the input type of the function, then arrow what is the output type of the function. So this is how, with this : symbol and the function name, we define the input and output type of a function, right? And similarly, you can load this and then you can use it, double 510. And if you want to check what is the type of this function, as always, you can type :t, then this function name, and Haskell says that, hey, the input type is integer and output type is also an integer for this particular case. Now, if you want to go back to our original code, which was the simpler double function without any type information, right? And if you load that again, just for some experiment, and then if you ask Haskell, hey, what is the type of that simpler double function, and Haskell says that the type information is input is A and output is also A goes to A. And before saying this input type and output type, Haskell also says something extra. It says that A is a number. Okay, so that is how to interpret this line, that double is the function name, then these all are the type information. Before reading this type information of input type and output type, we have the Haskell is also saying what is A, and A is a number type. So we understand that input is a number type and output is also the similar number type. That is how to interpret this last line, which is in green. Okay.